Hello. Welcome everybody. So, continuing this series of online seminars hosted by the Bootstrap collaboration. We are very glad to have Abhijit today telling us about modularity of supersymmetric partition functions. And so, thank you, Abhijit. The floor is yours.
Okay, thank you. Let me start the screen share. Can everyone see me and see the screen and hear me okay?
Yes.
Okay, fine. Thank you very much, Leonardo, for inviting me to give this talk. So this is going to be about a new type of modular property that partition functions in higher dimensions enjoy. So although the idea is quite general, it's easiest to make things concrete in the context of supersymmetric theories. So I will stick to supersymmetric partition functions and that too in 4 dimensions. So let me just start with some motivation. So we all know that partition functions of 2-dimensional conformity theories on torus enjoy modular invariance. This is due to the large diffeomorphism group of the torus, which is SL2Z, and the modular invariance, among other things, relates, for example, the density of operators at high energies to the contribution due to identity, and as a consequence, we get the celebrated Gadde formula. So this is just one of many usefulness of this SL2Z modular property of the CFT partition, 2D CFT partition function. Now, apart from Gadde formula, of course, as you all know, modular bootstrap has been effective in imposing bounds on the gap between the first excited state and the vacuum in 2D CFTs. So modular invariance in that sense has turned out to be quite powerful in constraining conformity theories in 2 dimensions. Now we know that in higher dimensions, CFTs obey constraints of unitarity as well as crossing, but natural question is, are there any other constraints that we are missing? Constraints perhaps akin to the 2-dimensional modular invariance. Okay, so by the way, can you see the cursor also?
Yes.
Okay. Now, if we are after a modular property in higher dimension, as in 2 dimension, it comes from the large diffeomorphism group of the manifold on which you're considering your partition function. So it seems that one should consider partition function in higher dimensions on a manifold which has a large diffeomorphism group. So for example, one could consider partition function on TD. The large diffeomorphism group, I mean the D torus, the large diffeomorphism group in this case is SLDZ, which is quite large and seems to be quite constraining. But unfortunately, such a partition function is not obviously related to the kind of things that we want to do, namely constrain the operator spectrum of the theory. The state operator map is only available for the Hilbert space on SD-1. So from this point of view, the partition function that we would like to constrain is the one on S1 times SD-1. In D equals to 2, this is the familiar T2, which turns out to have large diffeomorphisms. I mean, a big large diffeomorphism group. For D equals 3, the large diffeomorphism group of this manifold, namely S1 times S2, turns out to be Z2 times Z2. And that is not a very large group. So perhaps it's not as constraining as SL2Z. Of course, one could try to see implications of this group and one may find an interesting result, but just you don't expect it to be as useful. Now, the large diffeomorphism group of S1 times S3, that is in 4 dimension, is also quite small. It's probably Z2 times Z2, although I have not seen any statement to that effect in mathematics literature. And for D greater than 4, nothing is known about the large diffeomorphism group.
Sorry, how does the Z2 times Z2 act?
Yeah, so this Z2 times Z2, you could think of this as an antipodal map on both, either on S1 or on SD minus on S2. Okay. Sorry, I shouldn't say on both. Well, one is antipodal map on S1, and the other corresponds to pi1 of the large diffeomorphism group of S2. So the large diffeomorphism group of S2 turns out to be homotopic to SO3, or rather O3. And then it has two disconnected components, and you can do a loop which picks the two disconnected components, giving you the other Z2. So a similar construction can be done for S3, S1 times S3. Okay, so this means that if one wants to consider partition functions S3 times S1 in 4D, perhaps there is no hope of finding any modularity. But there is a hope, and that is because there is a very special mathematical function called elliptic gamma function, and it enjoys a very interesting property which I have described here. Okay, Z, tau, and sigma are the variables on which it depends. You can think of this as a function of Z with parameters tau and sigma, and it obeys this interesting property. As you can see, it is inverting the parameters. So in that sense, it is very similar to the 2D modular invariance that we looked at earlier. Here the Q is this polynomial cubic in Z, which is sometimes called the third Bernoulli polynomial as well. Now it just so happens that this gamma function is the superconform index of the chiral multiplet of R charge 0. So because it's an index, it's a partition function on S3 times S1. So what business is the partition function on S3 times S1 obeying this type of a modular invariance, obeying this type of property? So in fact, this property can be understood as a sort of covariance under the group SL3Z. And SL3Z is the large diffeomorphism group of T3. So there are natural questions, of course. Where is this modular property coming from, and where is this T3? And in answering these questions, we will discover a more general property of supersymmetric partition functions in 4 dimensions. Okay, so before we jump into properties of the 4-dimensional partition function, let us review more slowly the modularity in 2 dimensions. And because the focus of this talk is going to be supersymmetric partition functions, we will look at modularity of supersymmetric partitions in 2D, partition functions in 2D, namely that of the elliptic genus. For concreteness, we will take it to be, let's say, 2, 2 supersymmetric theories. Now, the elliptic genus is defined to be so in the RR sector. I take it to be in the RR sector because then I could talk about properties under the full SL2Z. Otherwise, I would have to talk about the properties under a subgroup. Now here, as you know, tau is the complex structure of the torus, and Z here is the background holonomy for the left moving R symmetry. Now, of course, if you have global symmetries in the theory, you could also turn on holonomies with respect to those symmetries, and then partition function would just be, a function of additional holonomies here. So this Z will be replaced by Zi. Now, so far in this discussion, we have the main player of this discussion has been the large diffeomorphism group SL2Z, but we would like to treat the group of large gauge transformations on the same footing as the large diffeomorphisms. So in this case, the large gauge transformations are generated by shifts of Z by 1 and by tau. These are the large diffeomorphism along one cycle of the torus or the other cycle of the torus. Now,
sorry, you mean the large gauge transformations?
Sorry, large gauge transformations, yes. Now, so that makes the group of large transformations to be SL2Z semi-direct product Z squared. This Z squared is the shift by 1 and tau that I talked about. It's a semi-direct product because the SL2Z acts on this Z squared. Its action on the parameters explicitly is given here, where G1 is the element of SL2Z, G2 is the element of Z squared. You can see this is the standard SL2Z that you know, and this G2 is nothing but N1 times the shift in one direction and N2 times shift in the tau direction. Now, if you had more holonomies, then you could shift those as well by 1 and tau, which would make the group of large symmetries SL2Z semi-direct product with a z square to the power r, where r is the rank of this global symmetry group. If I turn on holonomies with respect to the Cartan generators of all these of this global symmetry. Okay. All right. So it's nice to write this modular property of the elliptic genus like so. So here I have the partition function defined, computed the partition function as a function of the holonomy z and the complex structure parameter tau. And here the partition function is computed at its G1 inverse image. And the modular invariance would have said that this is precisely equal to this, but that is not so. There is a phase factor up to which these are equal. Now, this phase factor is important. It is a signature of the 't Hooft anomalies of the theory, as we will see soon. But just as a consequence of this equation, the phase obeys this equation. Okay, so you simply think of this phase as z divided by z at G1 inverse acting on the parameters. You put this here, and you see that this equation is trivially satisfied. Okay, so this is sometimes called the first group co-cycle condition or equation. Now, as I said, this phase phi g encodes the anomalies of the theory. In fact, you can compute this by considering a mapping cylinder like so. So you have a torus with z tau parameters and another torus with G1 inverse z tau parameters, and interpolating between them is a 3-manifold, and you can evaluate the anomaly Chern-Simons 3 form on this manifold to get this phase corresponding to G element. So you consider a mapping torus with group element G, and from here you would evaluate the phi G. Now, another way to see that this is indeed related to anomalies is that there does not there does not exist a redefinition of the partition function such that the new partition function enjoys exact modular invariance. Meaning, this phase you cannot just redefine z to z prime such that this phase goes away for all values of g. You cannot do that. And that you can see by trial and error, or there is a neat way of seeing that. You can consider two group elements, G1 and G2, like so, and just evaluate this particular quantity. Now, this quantity here is the thing that appears in the exponent here. So because this has to be obeyed, this needs to be 2 pi I times integer, and it is indeed that. So this equation is obeyed, but it is not 0. Now, if this were possible, that you could absorb all these phases into redefinition of partition function, then it is not difficult to see that this should have given you 0, which is not the case. So that is an immediate measure of the fact that phi g is an anomaly, and you cannot get rid of it by a local computer. Now, because of this condition here, you can see that once you know phi g on generators of the group G, then you can compute this for all group elements, because multiplying, this is just an equation that tells you if you know it for G1, you know it for G2, what is it for G1 times G2. So you can define the partition function in a way that phi g corresponding to all but 2 generators is 0. And these 2 generators is the S transformation and a shift by tau. Okay, and the coefficient appearing here, the number C, is the central charge. So a meromorphic function, which is the elliptic genus that transforms in this way, is known as the Jacobi form of weight 0 and index C over 6. Okay, and the classification of such Jacobi forms is an interesting problem in its own right. Now, for 0, 2 supersymmetric theories, or if you had additional holonomies turned on, a more general form of phases is obtained. And again, in the same way, they are computed from the anomaly polynomial of the theory as before. And then it's an interesting problem to look at this equation and take all the phi g's that come from the anomaly polynomial and analyze the space of solutions of this equation. Now, if the elliptic genus is a good stand-in for 0, 2 supersymmetric theories, meaning there is a one-to-one map, you may or may not believe that there is such a map, but it seems reasonable to assume so. then this solution space of elliptic genera is isomorphic to the space of 0,2 theories with a given anomaly polynomial. So in that sense, you can think of the 2D modular equation, which is this equation here, as a sort of a bootstrap program, meaning you want to constrain the space of 0 to theories with a given anomaly polynomial. So you would in effect constrain the elliptic genus that obeys this equation.
Sorry, there's no counterexample to two theories having the same elliptic genus, and
I don't know.
I mean, isn't there a famous counterexample for modular invariant partition functions in the bosonic case? This the idea that you cannot hear the shape of a drum.
For the bosonic case.
Yeah. I mean, there's this famous counterexample in 16 dimensions where you have two conformal field theories that have the same spectrum but different 3-point functions.
I see. Yeah, so in this case, yeah, so that could certainly happen, but I guess nevertheless, this problem is interesting in its own right.
Yeah, thank you.
Yeah, I don't know whether such things will not happen for supersymmetric theories. Yeah. Now, let's look at the mathematical structure of this problem a little bit closely and develop some vocabulary, and that will help us talk about the properties of the 4-dimensional partition function as well. So the elliptic genus is a meromorphic function, so let that space be n, and the phases that appear, the phases will appear all over the place. So the space of all phases I'm calling m, and because the partition function can be multiplied by arbitrary phases, the elliptic genus actually is not quite a function of n, but rather n mod n. Now the equation obeyed by the phases is this one, and is known as the first group cocycle condition, as I said earlier. Now a trivial solution to this condition would be to simply consider this. So this would be the solution in M itself. Now if this were the case, then that means we can make all the phases go away by redefining Z, because you just redefine Z by e to the I chi, and then it will absorb all the phases. Since this is not possible, e to the I phi j is not simply a co-boundary. It's a cocycle, but not a co-boundary, which makes e to the I phi j a non-trivial element of the group cohomology. So I'm not going to go too deep into talking, defining this group cohomology very rigorously, but the idea of the group cohomology is clear from these equations, that it obeys this cocycle condition, meaning it is closed, but it is not exact. And the notation here is simply saying it's the first group cohomology because it's the first group cocycle condition. It depends on G, so you can think of this as a form index. So the number of G's that you see here, I mean the number of G's that it depends on is the degree of that cohomology, and this G is simply the group in which this G lives, and M is the coefficient space because this is an element of M. Okay, so that makes e to the I phi j a non-trivial element of the first group cohomology, this one. Now, this also makes, you can ignore this if you want, this also makes the elliptic genus a non-trivial element of 0th group cohomology. Now you see the coefficients here are n over m, because as I said, the elliptic genus is an element of n over m. And this nothing but says the same thing that I've been saying, that you cannot redefine Z. You cannot quite write Z. You cannot quite get rid of all the phases to be one. Okay. Okay. So now I will move on to 4D and present the.
Can you tell us a little bit? What is the stage of this classification problem that you just outlined?
Yeah. So this problem has been considered for 2,2 theories, not for 0,2 theories that presented here, which was a more general case. But for 2,2 theories, and when you consider just the function of z and tau, I think Zagier has a book on this, and there he talks about the space of these forms for integer values of this integer value of this index, and you can classify this using what is known as the polar part. So the dimensionality of this polar part of the elliptic genus, the dimensionality of this space is known in that sense, but only for this particular type of problem. I don't know of any other more general statement about classification of objects obeying this equation. Okay. Yeah. So are there any questions on this 2D part? So it was kind of important to talk about this vocabulary a bit, because then we are in a position to state the main result about 4D partition functions, and it will not hurt to state it right now, and we can try to understand it as we go on. So yeah, this is what I say here. So let the 4D n equals 1 supersymmetric theory have a global symmetry of rank R, and we turn on background holonomy for each of them. Okay, so the group whose cohomologies will appear is now this one, which is SL3Z semi-direct product Z cube to the power R. Okay, so for 2 dimensions it was SL2Z semi-direct product Z square to the power R, but here 2 is replaced by 3.
So you're assuming you're computing the partition function of, but you're not assuming necessarily conformal invariance.
Yeah, I'm not assuming conformal invariance. This is going to be just for supersymmetric theories. These partition functions are invariant under RG flow. In that sense, they describe partition functions of the CFT, but they can be computed for non-supersymmetric, non-conformal theories as well. Very similar to this Rommelsberger type thinking. Okay, so yeah, as I was saying, here the group that appears is SL3Z times Z cube. So the thing that has to appear is T3. Okay, and with this group, we can say that the partition functions are non-trivial elements of H1. So the first group cohomology of this group, valued in this meromorphic function modulo phases. So because it's H1, they obey the first group cocycler condition. So because they're H1, first of all, they get a label, a group label, and they obey the first group cocycle condition. It is the condition that was obeyed by the phases in 2 dimensions. So this is the condition that partition functions now obey. Now, because they are elements of n mod m, this equation has a possible phase multiplication like so. And now this phase here it's 2 labels.
What is n? Can you remind us what is n and what is m?
Yeah. So n is the space of meromorphic functions, and m is the space of phases or entire functions. Nowhere vanishing entire functions.
Maybe you want to say functions on what?
Functions on these things, the functions of these things, the background holonomies and this tau. So in this 4-dimensional case, now it will be a function of some parameters. I have not said yet what those parameters are. Well, I've said them here. So this is going to be functions of Zi, and there are going to be 2 parameters, tau and sigma. So in 2 dimensions, we only had 1 parameter labeling the geometry. In 4 dimensions, there are going to be 2 parameters labeling the geometry, tau and sigma. And then there are background holonomies Zi. So these are functions of these variables.
So you are implicitly using the fact that this partition function only depends on the complex structure of the manifold.
Yes, right. And that has been shown by Cyber and friends. Okay. Right. So as I was saying, unlike 2D, this partition function now has a label G, and this also has a phase here. Now, just like in 2 dimensions, this phase, you cannot redefine this partition function z to z prime so that all these phases go away, just like in 2 dimensions. That is what makes it a non-trivial element of H1. And moreover, this phase that appears here now gets 2 labels, G1 and G2. This is not G1 times G2. These are 2 separate labels. That's because these, there are 2 separate gauge the group elements that appear here. And just again, by virtue of this equation, the phases obey this equation, just by virtue of this equation. And this is sometimes called the second group co-cycle condition, because it depends on 2 group elements. And then, as I said, you cannot redefine them away. Means there is no co-boundary type solution for phi, which makes this phase an element of second group homology valued in M, valued in phase. Okay. So I hope
you haven't quite defined yet what is this partition function which has a label G.
Yeah, I'm not. So that is going to be the main part of the talk. So I just said it here because we had the language to say it, and it's good to anticipate what is going to come. But that is why
maybe you'll say it in a minute. But the vanilla S3 times S1 partition function corresponds to what in this language?
G equals a particular element of SL3Z.
Not 1.
G is not 1. No. The identity would be S2 times T2. Partition function S2 times T2. Okay. So it will come soon. So I will analyze this group and this group elements soon. Okay.
Are you going to show why it obeys this co-cycle condition?
Yes, I will show that. Why this obeys this co-cycle condition. Yes, certainly. Okay. I hope so far. So this is the maximum map that would appear in the talk. I hope, and I tried to make it not so rigorous. Try to keep it simple. So I hope it's okay. If not, please do let me know. Now, yeah, just like in 2 dimensions, these phases here encode anomalies of the theory. Okay. So at this point, I would like to point out a caveat of all this, that this partition function ZG, which I said is a partition function, is not quite the partition function, but something closely related. Okay. Now, okay, so that the partition function, let's say, obeys this condition, then what is the modularity? How is it going to help us constrain the partition function? Okay. Now, so this, seems to tell us that if you know the partition function on the generators, then you can compute it for other group elements using this equation. But this also says that if the generators obey some relations, then you can evaluate this condition on the relations, and then that's a consistency condition on the partition functions. Okay, so that is what you can exploit to get constraint equation on partition functions. So in particular, an important constraint is the following. In SL3Z, there is an element Y that cyclically permutes 3 entries. So if you think of SL3Z as a 3x3 matrix acting on a column, 3-dimensional space, then there is an element Y which will permute 1 to 2, 2 to 3, 3 to 1. Without any minus signs. So in SL2Z, we are used to the minus sign, which is base element, but here we don't have a minus sign. And it obeys a Y cube equal to 1. Now, Y cube equal to 1, obviously, because it is permuting 3 entries cyclically. And now you evaluate this co-cycle condition on this relation, and you get a consistency condition for ZY. Okay. And for chiral multiplet, it turns out that this ZY is precisely the supersymmetric partition function S3 times S1. That is the superconformal index. This means this ZY is equal to the elliptic gamma function that appeared a few slides ago. This is a function Z tau sigma. And then this equation is an explanation of this mysterious property that the elliptic gamma function seemed to obey, which I have reproduced to be here. Okay.
Can I ask a stupid question? Why is Y
sure. Hi, Martin.
It's y to the -2 just not equal to y.
Yeah, you could write y here. Yeah, you could write y here, certainly. Yeah. Okay. Okay, so,
And I also
but what is interesting from this point? Yes, please.
So you mentioned that for the supersymmetric partition function that you need to choose this g in a particular way. Are you always going to choose g is equal to y, or does that depend on the theory that you're choosing?
No, so this will not depend on the theory that I'm choosing. I'll always choose, you mean to get constrained equations, right?
Exactly.
Yeah, so the way this is going to work is as follows. So as I said, only knowledge of ZG for G being generators of this guy is sufficient. And moreover, I will get some of these generators, ZG for some of the generators equal to 1. And then the only independent, in some sense, degree of freedom would be Zy. So this is the only unknown, and this constraint in this way. And then there are some other constraints that I'm not going to talk about. But yeah, so it's not going to be, sorry, to answer your question, is not going to be dependent on the theory, which element I choose. Okay. So yeah, so the nice thing about this way of looking at it is that this equation here is not just true for the chiral multiplet. It's true more generally for more interesting theories as well. And we will conjecture, although this can be computed using Chern-Simons phi form. I've not done it so, but we can conjecture that this phase P is essentially the 't Hooft anomaly polynomial of the theory. And this conjecture is consistent because it reduces to this Bernoulli polynomial Q in the case of chiral multiplet. Now this equation lets us ask the same question as we did.
Sorry, but this is something that one could just compute, right?
Yeah, so P of t can be computed, yes, using the Chern-Simons phi form. Yeah, I agree. P or more generally, all these phases one can just compute. And I will outline how would one do so also. Okay, so this question, this equation lets us ask the same question as we did in 2D. What is the space of all partition functions that obey this equation for a given polynomial P of t? So this is a question very similar in spirit to the 2D one, and can be thought of as a bootstrap type question. You are given an anomaly polynomial, and then you ask, what is the space of partition functions with that anomaly polynomial?
Is this anomaly polynomial to be thought of as anomaly associated to the gravitational? Is it for the gravitational anomaly to the element?
Yeah, it's for the gravitational. Well, yeah, it's the while anomaly is what appears in addition to the standard 't Hooft anomalies. But because we are looking at supersymmetric theories, you need not talk about while anomalies, but you could simply look at anomaly of the R symmetry. Supersymmetry relates the two. So you can just think of this P of t as an anomaly polynomial involving R symmetry and other global symmetries.
Okay, thank you.
Yeah. Okay, so now I describe the origin of this first group cocyclic condition that the partition function must obey. In particular, I will explain where the T3 comes from. Now, this comes from thinking S3 times S1 as being glued, as being obtained by gluing 2 copies of solid 3 tori. Okay, so more familiar perhaps is the gluing of two solid T2s to obtain S3, and you simply take a direct product by S1 on both sides to get this picture here. So in other words, the one extra circle, this just goes for the ride. So you simply write this S3 as gluing of 2 solid T2s. Okay, and the boundary of this solid T3 is of course T3, and this is the T3. This is the large diffeomorphism group of this T3 is what gives us SL3C. Okay, so I have drawn some pictures here. So this is just to show you what kind of gluing you need to do. So this is my way of drawing one copy of solid T3, which is T2, which is this cycle times this cycle times a disk, which is a solid T3, and the same type of manifold here. But this indicates the gluing. The gluing is not, you're not gluing the contractible cycle with the contractible cycle, but rather you are gluing the contractible cycle with the non-contractible one. This is the standard construction of the S3. If you ignore this gluing here, this here is the standard construction of S3, and then this just goes for the right. So in this way, by gluing two solid T3s, you can construct S3 times S1. I hope this is clear. Now, instead of gluing with this S element, in this subspace, the standard modular S element, you could glue by the identity element. So the contractible cycle is glued to the contractible cycle and so on. And then what you get is S2 times T2 clearly, because this is a T2 and this together gives you S2. More generally, you could glue by a diffeomorphism of this T3. And in doing so, obtain a manifold which I've labeled as MG. So this manifold includes all the length spaces in addition to these two examples that I have drawn separately. All the length spaces LPQs. Now, I don't quite know whether it also can produce other manifolds by such gluings. It would be nice to analyze this.
Abhijit,
Now,
question?
yeah.
So can you explain why the first picture corresponds to the element Y? Naively, Y would permute all three, right?
Yes.
So look at S4. So it seems to make better sense to consider mapping torus of T3 given by these elements. Then for Y, you will get indeed S1 times S3, but for identity, you will have T4.
Mapping torus. No, I'm not considering mapping torus. No. Sorry, I didn't quite understand. Understand what you're saying. So you could think of this as an element, which is an S element here, or you could also consider this as a cyclic permutation of these three. So in that sense, Y also gives you the S3 times S1, except that the parameters will now be not the standard ones, but something else.
Sorry, why? I thought if you use Y, you will just get S4 here.
S4? S4, no, I don't see that, no. I don't think you can cut the S4 into two solid T3s. There is no way of cutting S4, I think. Yeah, I don't think there is a way of doing that. But yeah, I would, I don't, we could talk more about it also. But S4,
how can you have S4? S4 doesn't have a complex structure.
Yeah, in particular that is the reason. Okay, fine. So by gluing with an element G, more generally, you get this manifold MG, which consists of all length spaces. And Cyberg and friends have told us that in order to preserve supersymmetry on all length spaces, the R charges must be even integers. So if they are not so, you could add some global symmetry to the R symmetry and make them even integers. But this particular property will not be so important for us. Okay. Now, the partition function ZG on manifold MG, yes.
What happens for theories for which you cannot choose integer R charges?
So that is probably a constraint on this construction. So this needs to be possible. If it is not possible, then you cannot do this.
Okay.
Yeah.
So do you think there are similar constraints or for those or?
But can you not always do it?
No, say you have a theory which doesn't have global symmetry, but it has non-integer R charges.
Yeah. So for this construction to work, you would need at least some choice of R symmetry which is integer. But that choice really wouldn't really matter. You just need to have an R symmetry with which the R charges are integer.
Sorry, but if we want to study the superconformal index don't we have a canonical choice to make for the R charge when the infrared theory?
Yeah, so yeah, so you could go back to that R symmetry, but for this construction to work, you need existence of the integral R symmetry. It will not play a much role, but at least this needs to exist. And then you can go back to the standard superconformal R symmetry.
But are you constraining the usual index or some exotic index? That's the question.
No, at the end of the day, it's going to be the usual index. But as Shlomo was saying, it will be required that there exists a choice of R symmetry, which makes all the charges even integer.
Abhijit,
Just to
may I ask?
put all these theories on the length spaces, basically. Actually, you could do away with even integers. You may only require it to be integers. That suffices. Yes, because you don't. So the even integers are required only if you want to put this on LPQ for Q not equal to 1. But the constraints that this partition function needs to obey, the modular constraints, we don't really need to put the theory on LP2 or 3 or 4. That's it. Yes, please.
So is it guaranteed that for any G, MG has a complex structure, or almost complex structure?
Yeah. Because I told you the list of spaces. I think it's just the length spaces and these two. Okay. Now the partition function ZG on manifold MG can be thought of as the inner product of the bra on the left with the ket on the right. So I'm denoting bra with these parameters because that is what controls the geometry here on the left, and the ket is G1 inverse, G inverse times these of these parameters, and then the partition function is this inner product. Now, the Hilbert space of the theory on T3 is infinite dimensional, but so I'm not going to describe this geometry in detail, but what is going on is a partial topological twist on both halves. Now, on one half you have topological twist, on the other you have anti-topological twist, and as a result you can take this cigar to be infinitely long on both sides and effectively project onto the ground states on T3. And the subspace of ground state is finite dimensional for supersymmetric theories, at least for gauge theories. And this is an important simplification that occurs in supersymmetric case. So
sorry,
later,
a couple of first going back to Du's question. So are you saying that if you just swap the two circles in your building block, you're getting the same manifold? So it's
if I swap these two?
No, the other two circles that are just by themselves.
Yes. Right. Mm-hmm. Yeah, exactly. But you need to, you always need to consider this at different parameters, right? Because this gluing needs to be compatible.
Mm-hmm.
So you would end up taking the parameters to be something else than in this picture.
Okay. And the other question, no, you can go on to the next slide. So you said that there's a topological twist. So did you modify the problem? I thought you were considering physical partition function.
Yeah, these are the physical. Well, physical meaning there is one way of preserving supersymmetry, n equals 1 to supersymmetry on these length spaces, or the S2 times S1 and S3 times S1. And the right thing to do is to do this topological twist. So once you glue this, you will end up with a standard partition functions.
Okay.
Yeah. So the fact that you can elongate this cigar and project onto the ground states, which is a finite dimensional space, is an important simplification that occurs in the supersymmetric case. Now, a more general observable would be to compute what one would call partition function matrix And that matrix is one where you have inserted supersymmetric defects at the core of the solid P3s. So at this tip here and this tip, let those defects be I and J. And if you compute the inner product, you would get something like a partition function matrix. And this is a more general.
Sorry, can I ask again?
Yeah.
Actually, so in 4D theory, you can consider four-dimensional theory on a torus times two-dimensional sphere, and these are different backgrounds, whether you turn on topological twist on the sphere or not.
Well, you cannot. There is only one way in 4 dimensions. You cannot do it in 2 ways. So in 4 dimensions, for example, if you want to preserve n equals 1, you want to preserve supersymmetry for n equals 1 theory on S2 times T2, then there has to be a 1 unit of R symmetry flux through S2.
Okay. But so in 3, for example, in 3 dimensions, you can do it in different ways.
Somehow different in 4D. Yeah, true. Okay. Different in 4D. Yeah. Okay. Now. Yeah, so I say that this is a more general observable. The advantage of this is that you get to span the Hilbert space here, the effectively finite dimensional Hilbert space. So you would need to consider only n defects because n is the dimensionality of the effective Hilbert space. Now instead of defects, we will do something else. We will pick an orthonormal set alpha on T3 and define the state like so. Okay, and we will compute the partition function in this basis. And it is given like this. And because this is orthonormal, this partition function matrix is a diagonal matrix. The wave functions here in the alpha basis are known as the holomorphic blocks. Okay, and this partition function here, the diagonal entries of this partition function matrix is known to have interpretation as the partition function in a given Higgs vacuum. Okay, so Wolfgar and Yoshi, that they have worked on this among other people also, and these Higgs vacuum are also labeled by this alpha. Now from here you can derive the cocycle condition quite easily. You just think of ZG1 G2. I'm just focusing on a particular diagonal element, so I have alpha, and this is the inner product, which is this, and here I insert a complete set of states and normalize in this way. And I get this one. Okay, and now if I define I define a normalized partition function like so, which is the standard partition function divided by Z1 at G inverse tau, then it is the normalized partition function that obeys the cocycle condition. So when I said I lied a bit, it is in this sense that the thing that obeys the one cocycle condition is not the partition function, but rather alpha component of the normalized partition function. Okay, is this clear? Now, in this construction, you don't see the existence of this phase that I talked about, but one should a priori allow for such a phase, because when we do this construction, we are assuming that the state here is labeled by these parameters in a unique way. But it need not be the case, because if one has a Berry connection on the space of parameters and that Berry connection is curved, then one cannot quite associate a specific state to a specific point, because it will pick up a phase as you go around and come back to the same point. In fact, the phase that appears in this equation can be associated to a path which takes the parameter tau to G1 times tau to G2 times G1 times tau and back to tau. And the phase e to the I5 G2 is precisely associated to this path. So this phase will pick up the Berry curvature from this path, and then you should allow for such a Berry curvature, and it will obey the consistency conditions that result from this equation. Now, so you can also, because I defined this holomorphic blocks already, so one can think of, so in 3 dimensions, for example, there is a prescription of constructing the partition function by taking the product of holomorphic blocks. If you try to do it here, you get this equation. So you have this partition function, and it is given by the product of holomorphic blocks. This was simply this, and this is defined to be the left holomorphic block. defined to be the right holomorphic block. Okay, and if you do this, then the normalized partition function will simply be given by this exact expression, cohomologically exact expression. So you see, this equation here seems to suggest that ZG is not quite non-trivial in cohomology, but rather is a co-boundary. Meaning, if for any choice of B, the ZG will obey the first group Coset condition, and moreover, all the phi's will be 0. Okay, so if this gluing equation, so if this equation that expresses the partition function as product of holomorphic blocks is correct in 4D, then this would necessarily mean that the normalized partition function is trivial in cohomology. So we will show that this is not the case. So the gluing formula to obtain the partition function with the holomorphic blocks is not quite true. It is only true for certain G's and not for all G's. Yeah, that's what I said here. Now, before we do that and consider a concrete example, let us look at the SL3Z in little more detail. By the way, how are we on time? Are we strict?
Well, in principle, we have 10 more minutes. How much more time do you need?
10 more. I mean, 20, that is in total. if that's
Sure. Well,
okay, fine.
You negotiate. I don't know. Try to.
Okay. I will try. And this is assuming that I speed up.
Okay.
Okay. So let's look at SL3Z in a little more detail. So because SL3Z is going to is going to play a main role, an important role in doing all these things. So we are thinking of SL3Z as a 3x3 matrix acting on this column vector, 1 sigma tau. These are lengths of these cycles. So one can think of this sigma tau to be complex parameters, but it's just convenient to take this T3 to be a rectangular T3. So and then you just think of sigma tau to be the lengths. So that is what I will do instead of taking any slanting, but one can do that also. And now this SL3Z, the 3x3 matrix, is acting on this column vector. Now let us define Tij to be the matrix which has 1 on the diagonal and 1 at ij entry and 0 elsewhere. So T12 is this, T23 is this, and so on. Now in mathematical literature, SL3Z is taken to be generated by Tij subject to some relations. And that's the standard presentation for SLNZ. But for us, we will pick a different presentation, the one which will help us make contact with the different SL2Z subgroups. So Sij be the modular S matrix of the SL2Z subgroup that acts on ij space. And then SL3Z is simply generated by S23, meaning the one that does the S transformation here, and S13, which does the S transformation here, and T23, which mixes the 2, 3. And to generate the ZQ part, we append this list of generators by T3, which is Z going to Z plus tau. Okay. Now, an important, there's an important thing that one must notice. So this SL3Z has a very special subgroup. So this is a subgroup of large diffeomorphisms or large gauge transformations of this boundary T3 that extends into the bulk. So as a result, they end up being the large transformations of this entire manifold, not just of the boundary. And because they are large transformations of the entire manifold, the wave functions on this need to be invariant up to a phase under the action of this subgroup. Now this is the diffeomorphism, as I say, of the whole solid T3. Yeah. So this makes so you can see that this makes that the normalized partition function with the H element, which is a large transformation that can be extended into the bulk, should be equal to 1. Should be equal to the 1 corresponding to the identity, and the normalized partition function for the identity is 1. And this subgroup is this one, and it's generated by S13. I can give you some intuition about this, but let me proceed for now. So it is this subgroup here. But as I said, the nice thing about this observation is that you can get for free this condition that is head hat of H, where H is all this stuff, and the stuff that is generated by this is 1. So already you know quite a lot about Z hat G's, because you know them for all H's. In fact, if you look at this set of generators, The only stuff that is not in the H is this one. The S13 is in H, T23 is also in H. So that means you only need to compute ZG of S23. Yeah, this is what I say here. Now, so this was about normalized partition functions. But if you want to get to physical partition functions, you would need the normalization factor, namely the identity term, which is where you just compute the Z2 times T2 partition function. So all this program has only two main players, which is Z hat S23 and the S2 times T2 partition function. And from there, you can generate all of this. Now let's go to an example. So chiral multiplet of R has 0. You have, the stuff that was.
I know you're in a hurry, but you shouldn't be. So the ultimate claim is that so long as you have, say, global symmetry, then you can always readjust the art symmetries to obey the constraint that you want, and you can play this game and ultimately constraining the usual vanilla superconformal index.
Yeah.
Is that true?
Exactly. Exactly. Yeah. Exactly. Okay. So as I said, that we need two things. We need the partition function with 1, meaning partition function S2 times T2, and the partition function S3 times S1. And for chiral multiplet, we know both these things, and they are here. And from here, you can consider Z hat S23. And with that, and all the Z hat H being 1, you can multiply all these things any way you want and generate partition functions on all MGs. These include length spaces, LPQ, with you can even turn on background flavor symmetry fluxes, which was the job of the shift operators, T1, T2, and T3.
So this works? You checked it?
Yeah. Yeah. Now, I should have written that. Now, so this is about generating the stuff that you don't know from the stuff you know. Now, how about constraining? Let's say you don't know this. How about constraining? So where are the constraints? Can you constrain these things? Moreover, the normalized partition S23, as I said, will get constraints because you will evaluate the first co-cycle condition on relations obeyed by generators. So in particular, it turns out to swap S23, Z hat S23 for Z hat of Y. There is a simple relation that relates the two. And then clearly there is a constraint that Z hat of Y must obey, which is this. Okay, so this is a constraint, this is a self-consistency condition on Z hat of Y. Now, in addition to this, there are some other constraints that I have not written. So this, if you wish, is like a constraint under S transformation in 2D case, but there are constraints coming from T transformations and also ellipticity constraints and so on. So Z hat of Y indeed obeys analog of those types of constraints as well. Now, so you can see that the Z hat of Y turns out to be the elliptic gamma function, as I said. And there is a mathematical paper by Felder and Marchenko. They show that the Z hat of G indeed forms a non-trivial element of H1 and this first group cohomology. Now let me discuss, going back to the holomorphic blocks, this claim that this gluing procedure only works for some G's and not for other G's. So this is not a universal prescription. The holomorphic block is for our chiral multiplet R has 0 is known to be this, and we expect the action of H, as I was talking about, is a special subgroup. Action of H on this holomorphic block to be trivial because it's a large transformation that can be extended to the bulk. Now it turns out you can check explicitly that the action of S13, S21, and T1, which are elements of H, is not trivial on this one. Okay. So alternatively, you can construct Z hat of H, and for all these three things, it is not equal to 1. But from physics, you know that it should be equal to 1. So in what this means is that the holomorphic block formula of constructing the partition function by gluing the two holomorphic blocks gives a local trivialization of a cohomologically non-trivial element. But it's only a local trivialization. It is not valid globally. That is, it's not valid for all G's. Now, yeah, so now we go to a slightly more complicated example. So the partition function of supersymmetric gauge theories. So it admits sum over an expression in terms of sum over Higgs vacua, like so. And one can show for gauge theories that the z hat of y, which is what was getting constrained, is simply equal to the perturbative part of this sum.
Sorry. So these are Higgs vacua of the three-dimensional theory?
Yes. No, the four-dimensional theory. Higgs vacua of the four-dimensional theory. Honest theory. Why do you say 3D? We didn't go to 3D.
Sorry, no, I just got a bit lost. So what is this Higgs vacuum? Can you say it more slowly?
Yeah, so you could write down, BPS equations for n equals 1 supersymmetric theory, and then there's just a vacuum which breaks the gauge group completely, turns on expectation
There's a little bit confusing.
for
For Danico 1, we usually don't distinguish what is Higgs branch, what is Coulomb branch. I'm unclear.
Sorry. Well, this the fundamental matter gets a wave in this vacuum. Okay. There is at the technical level, one way to.
This is a definition that makes sense for Lagrange. This is a definition that makes sense for Lagrange and gauge theory.
Yes. So this is a supersymmetric gauge theory. Yes, exactly. Yeah. So in particular for non-Lagrangian theories, you don't quite know whether such an expression exists. Okay, but well, okay. So I should say that such sum over alpha would exist, but you don't quite know. What is the index set of alpha? What is the physical interpretation for it? You don't know. One doesn't know for this for non-Lagrangian theories. But the sum, this expression must exist. That just follows from decomposition of the partition function over the T3 channel that I was talking about. The kind of cutting and gluing that I was doing. You could simply consider the gluing of these solid T3s, and you insert a complete set of states. And from there, you can get this expression. But whether this sum is infinite in that case or not, that in particular is also not clear to me. But for gauge theories, you know this. Now, so as I was saying, you can show that this z hat of y, which was the main player, is equal to this perturbative part in cohomology. So that means this z hat, this ZP, this ZP obeys the modular condition that I wrote down earlier. Now, for gauge theories, this ZP turns out to be product of elliptic gamma functions, and it is easy to check that it satisfies all the constraints that come from this first co-cycle condition. Now, so one can it's interesting to think of this as from the bottom-up point of view. So you want to solve for this is something that I already said. You want to solve for these z hats given the input of this e to the I phi g, and see whether there are any other solutions apart from the gauge theory. This classification program that I was talking about earlier. Okay, so now one can also rederive the Cardy formula for four-dimensional supersymmetric gauge theories that has appeared recently in the literature by Kim and these people here, Sunil Murthy and so on. That goes as follows. So as I said, the perturbative part, so I should say that this derivation is valid only for gauge theories to begin with, but perhaps one can try to do more general things and try to prove this formula for non-Lagrangian theories as well. But right now I don't know how to do that. So I will just mention how this is done for gauge theories. So for gauge theories, this z hat of y is equal to the perturbative part in cohomology. So it must obey this. And the high temperature limit now is taken by taking sigma and tau to 0 from plus I direction, plus imaginary direction. And in this limit, you can show that this and this term go to 1. Slightly non-trivial, but you can show that this goes to 1. And so that means the high temperature limit of this object here gets related to this P. Now, this is not quite the high temperature behavior of the partition function, because in the gauge theory partition function, in addition to the perturbative part, there is also a vortex part. There is a ZV. So how about that? What happens to that in the high temperature limit? So there, the contribution coming from ZV is subleading. And intuitively, it's clear because the ZV essentially measures two-dimensional degrees of freedom. You know, the stuff that only lives on the vortex. So it's expected, you could expect that to be subleading. And you can take this limit of this this side P, and you get this formula, which has appeared in these papers. And and related to what the comments that Leonardo has been making, you know, in order to get to this formula, you need to take the R symmetry to be an integral R symmetry. But once you do that, you can simply shift the global symmetry, shift the R symmetry using the global symmetry back to its superconformal values, and restore and get to CLA, which are related to the R symmetry anomalies, superconformal R symmetry anomalies. In this way, you obtain this formula. Okay, so
do you get to reproduce? Do you get to reproduce this this whole recent story of? You know, there's now a little bit of a lot of activity on the high temperature limit of the index, and in particular being able to reproduce this n-squared behavior for black hole entropy. Is that all contained?
Yeah, right. So yeah, that is contained, because if you just compute this for n equals 4, it's not 0. It goes as n-squared. This stuff here. I think that is one of the main points of this Gadde formula, that C equals A, right, in n equals 4. So because this doesn't quite cancel completely, there's an n-squared here. And that tells you that it goes like n-squared. Okay, so now, yeah, let me comment on the relation between the geometry of the problem and this modularity. So this is going to be slightly schematic. Get to the end. So let's go back to the 2 dimensions. The partition in the 2 dimensions, the partition function that we consider was on T2, but you think of that T2 as a fibration on a point. Okay, so you have a point and there is a T2 fibered over it, and then this is equal to you know, a fibration of a different T2 on a point, you know, the G transformation, and you compute these phases that appear by evaluating the anomaly Chern-Simons 3 form on a mapping cylinder, which I've denoted like so. So here you should think of this as an interval on which a T2 is being fibered. Here it's fibered with parameters tau. Here it's fibered with parameters G inverse acting on tau. And this line here is the fibration of T2 that interpolates between them. And evaluate this Chern-Simons form, you get this. Okay, so this is the structure of the 2-dimensional modular equation. Now in 4 dimensions, you know, the partition function is on T3 fibration over an interval. This gluing picture that I presented, you can think of this as a gluing of 2 solid T3s, but equivalently, you can also think of this as a fibration of T3 on an interval, with one cycle shrinking on this side and the other cycle shrinking on some other cycle shrinking on the other side. So this I have presented like so, and this phase e to the I phi G1 G2 then can be computed by evaluating the anomaly phi form on a T2 fibration. Sorry, T3. This should be T3 here. T3 fibration over a disk. So this I have denoted the disk like so. So let me try to explain this in a slightly more detail. So I have here a 4 manifold. This should be thought of as a 4 manifold. And what is this 4 manifold? There is a T3 fiber over it. Okay. And so you have a T3 whose your cycle is shrinking here, and another cycle is shrinking here. And which cycle is given by this G1 times G2. And now this vibration, I'm splitting it into 2 parts, one from 1 to G1 and then G1 to G1 G2, like so. And if you see what the boundary of this space is, so So in some sense, you evolve this 4-dimensional picture into 5th dimension so that it ends on this boundary. And in this way, you can get to the 5-dimensional space, which is a T3 fibration over a disk. And it is, and these values G1, G2, and G1, G1 and G1, G2, they describe the fibration in totality. This just describe the T3 fibration. So this is the power of group cohomology, which I will not go too much into. But the picture, the meaning of this diagram is that they just totally describe the T3 fibration over a disk. Okay, so continuing along the same lines, there is a conjecture for 6D. You can consider supersymmetric partition functions on T4 vibrations on a disk in the same framework. So now this is our 6D partition function, and that should be related to its decomposition like so. So this involves 3 partition functions of this type, and then and this stuff here is the boundary of this 7 complex, or this this 7-dimensional manifold, which is a T4 fibration on this 3 ball. Sorry, this has been a bit fast, too much time. But yeah, from here you can compute these phases. And in fact, the index of the chiral multiplet in 6 dimensions is what is called the double elliptic gamma function, and that indeed obeys this condition here that I have written down, with the phase that you can actually explicitly either compute or along the lines of the 4D, you could conjecture it to be the anomaly polynomial, and this precisely matches the anomaly polynomial.
What's the reason you skip odd dimensions in this classification, in this hierarchy?
Yeah, that's a good question. You could consider odd dimensional things, although I think because the anomalies don't exist in odd dimensions, then modulo some discrete things that one needs to think about more carefully. I think that is the reason why, for example, the holomorphic block decomposition works in odd dimension for all G's, because there's just no e to the I phi G that could appear. So in that sense, you could consider this in odd dimensions, and then it's slightly perhaps simpler in that you won't have this phase factor. Yeah, so I have not thought too deeply for odd dimensions. Sorry, I think there is a question here, no?
Yes. Sorry, I just wanted. When you say that in 4 dimension this holomorphic block proposal is not working, I mean, we put forward a proposal where we actually say that we need to strip off precisely the contribution of the anomaly to see that the partition function, that it could be on S3 times S1 or S2 times T2 can be factorized. So we are not claiming that it is already factorized in blocks. We have to say that if you want to see the factorization, you have to remove the anomaly. So if you buy that, then okay, maybe it's just a question of names. So you would say it works only if you remove it, but we are not claiming that it works without removing.
Okay, I see. Okay, thank you for the clarification. Yes, so I was saying in more naive terms. I need to see exactly the proposal, but yeah. Thank you. Okay, so now this is the last slide. I'm ending with Outlook. Sorry for going over time. Okay, so here, this is just the emphasis again on the bootstrap nature of this problem. One can try to fix all these phases by computing them 5D Chern-Simons theory, and then try to analyze the space of solutions to such equations. Yeah, and then because this kind of relates either the perturbative part or the what I call the normalized partition function, it doesn't directly make contact with the physical partition function. So it would be nice to, for gauge theories we have a way to do that, but it would be nice to do this more generally so that it directly makes connection to the partition function itself, which would be useful for non-Lagrangian theories, and it will really help us investigate questions like bound on the gap, etc. Now, yeah, so here as I commented early in the talk, that this gluing condition also works for non-supersymmetric theories. The cumbersome issue is that the Hilbert space on T3 is infinite dimensional. So you don't quite know. So here it has a nice interpretation as partition functions on Higgs vacua. The things that obeyed modular properties were the partition functions of the Higgs vacua. Here, it's something that has not been analyzed. But you could imagine that instead of considering the full partition function, you could consider it in some channel. So in the T3 channel, you just let a particular eigenstate run. It would automatically be some orthonormal part of an orthonormal basis. And then for that channel, it's some sort of a block. It's kind of like a conformal block. In conformal block also you let only a certain operator run in the middle channel. So similarly in the T3 channel, you let a particular state run, and for that is the quantity that would obey the SL3Z properties that we discussed in this talk. And I think it would be useful to do this even for a free theory to begin with, just to see the structure of these blocks. And one could also consider partition functions on other torus fibrations, such as T2 fibrations on D2, in 4D, or T5 fibrations on an interval in 60. Now, if this all the geometric picture gives a very natural set of conjectures for the modular properties of these guys. So one really needs, basically one has to see is what happens to supersymmetry, whether supersymmetry is preserved in all these constructions or not. But the conjectures basically is that the first guy would be the second group cohomology of SL2 times Z2 to the power R, and the second guy, which corresponds to T5 fibrations on an interval, would be the first group cohomology SL5Z times Z5 to the power R. So this, I think it would be interesting to explore these possibilities further as well. Okay, I'll stop here. Thank you.
Thank you. So any further questions?
Do you have an example of a computation of this partition function on the manifold with interesting complex structure moduli to see the complex structure dependence?
So the sigma and tau are the complex structure moduli.
Yeah, but it's kind of too simple. So how about K3 times something?
I see. No. So for now, in this particular framework, more interesting cases than that I had not thought about.
I mean, you seem to be using some kind of toric structure. You always have torus vibrations.
Yes.
Does it have to be toric, or do you need torus symmetry at any point?
No, the torus is because it leads to a big large diffeomorphism group, like SL. For TD it would be SLDZ. But you could imagine fibrations not of tori, but T2 times something. So at least have some factor of torus, and the rest could be something else.
Well, K3 has interesting large. I mean, K3 has an interesting group.
But you're thinking of K3 as a target space, or
no, because, as a space-time.
Yeah. So you want to define theories on K3.
It seems like the construction it looks more combinatorial than it should be, because if the partition function is really sensitive to the complex structure, it should not be possible to simply glue things out of blocks placed anywhere you like. It should be more sensitive to.
Well, at least in this case, where you just have complex structures which are sigma and tau, then this gluing is compatible, because from the work of, as I said, Natty and friends, that supersymmetry can be preserved on these manifolds and can be preserved for any value of these complex structures. So at least in this framework, it's all good. But more generally, I don't know.
Well, I would say that even much earlier, there were works when people found holomorphic sectors in supersymmetric gauge theories on complex manifolds. This was called BC beta gamma systems. And then there were all kinds of relations obtained on relating holomorphic blocks to anomalies, to chiral Lagrangians, and all. So there, it was believed that you really need to explore more complicated complex manifolds to see the full structure of the theory, to see all constraints. Like in 2 dimensions, it actually, even though if you might be interested only in genus 0 correlation functions, it actually, when you just think about all possible geometries in 2 dimensions, that imposes powerful constraints.
Yeah. It could be that. Yeah. For example, yeah. Instead of perhaps maybe you're saying instead of T2, you could consider higher genus vibrations and things like that. Maybe.
Yeah. But also, I mean, there are plenty of elliptic K3s. So locally, it looks like a torus vibration over some base, but then it's important to glue things together. So it forms K3, not S2 cross T2 or something. My other question is, the reason I'm asking about this is that if it is true that you can actually compute these partition functions combinatorially and then test for consistencies with various anomalies, maybe you can actually test whether a manifold you're working on has a complex structure or not. Because there is this famous question whether the 6th sphere has a complex structure. So if you can compute consistently your partition functions on the 6th sphere, maybe that would be a hint that it has a complex structure. Or on the opposite side, if you can scan through all theories under your control and you find inconsistencies for all of them, then it's a good hint that the 6th sphere does not have a complex structure.
Yeah, that's interesting. Yeah, that would be nice to look at. Right now, I don't have anything to say about it, but yeah, thank you.
So does this shed any light on the defects in n equal to 2 superconformal field theories, which should correspond to interesting solutions of this modular differential equation for the Schur index? Or
So I think just of the Schur index, the kind of thing that Shlomo had worked on, I think this property should, although I've not checked explicitly, this property should reduce to, if for the n equals 2 case, if you take the Schur limit, should reduce to the thing that Shlomo discovered. But more generally, with the defects, etc., I don't know. But yeah, but maybe this is what, maybe it could reduce to even the model properties of the characters corresponding to the defects also. I don't know. But vanilla Schur index, it seems very natural just from the geometry.
Okay, we're a bit out of time. So any other questions? Okay, if not, thank you, Abhijit. Very nice talk. And we'll see you next week. Thank you.
Yeah.
Thank you.